We've seen with stop and wait ARQ, same concept as stop and wait flow control, but we now have this retransmission scheme. Send a data frame, wait for an ARQ. If you don't receive an ARQ within some specified period of time, retransmit. Okay, that's the basic retransmission, a positive acknowledgement. That is, I expect an acknowledgement. If I don't receive one, try again. The reason we have sequence numbers, so we introduce also a sequence number. The reason we need this 1-bit sequence number is for this case where our ARQ is lost. If we didn't have a sequence number, if we just said data, 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 then the receiver would not be able to distinguish between the old one and the new one. So we need a 1-bit sequence number with stop and wait ARQ. We don't need larger, 1 bit's sufficient. Sometimes called alternating bit because the bits alternate between 0 and 1. What else do we have? If we receive, although we haven't shown it, if we receive a frame which is damaged, we treat it as being lost, and the same scenario arises. Similar to stop and wait flow control. Stop and wait ARQ is very simple, but inefficient. Yep. Damaged data means I receive a frame, but I detect that there are errors in that frame. Although we didn't cover error detection, we skipped over that topic. But remember, there are ways like parity checks, CRC checks, that the receiver can detect if there are errors in a frame. Okay? So a damaged frame is I receive a frame, 1,000 bits, I recognise 10 of those bits are wrong. Then I will discard that frame and treat it as lost. So normally we treat damaged frames and lost frames the same. You can calculate the efficiency if, for example, this packet is lost, then we can look at the performance in terms of how long does it take to deliver our data. The same with flow control. But now we need to know the timeout period. That's normally a parameter in the protocol. That is, it's given. We say the timeout interval is 10 milliseconds. Then we know if we start at this time, then 10 milliseconds later we'd retransmit. So a timeout interval is a parameter of the protocol. And same as stop and wait flow control, it's inefficient in cases where we have a large propagation delay relative to the transmission delay because we spend time not transmitting. But simple. Any questions before we move on to the improvements or the alternatives? And similar to flow control, the improvements are based on sliding window. Send multiple frames. Any questions?
Is it already 1-bit sequence or depend?
In stop and wait ARQ, we just need 1-bit sequence number. The sequence number is only needed for this case, really. The reason we need a sequence number is so we know. Here we receive data with sequence number 1. Then we receive data with sequence number 1 again. We know it's the same as before because it's the same sequence number. So we discard it. If we didn't have a sequence number, it would just be data, data, and data again. We'd receive this data again, and there's no way for the receiver to know, is this a retransmission of this one, or is it new data? So that would be a problem. So in this case, we introduce just a 1-bit sequence number to know whether the data we received is a retransmission or not. So we just need 1 bit. It's either is or it is not. You don't need longer sequence numbers. Any other questions? Is that a question? Or is that the problem with... Sure? Any last questions? So if you look at examples from quizzes and exams, I would give you, for example, the timeout period, how long you have to wait until you retransmit. That's some value I would give you. And, all right, when is a data frame or an ARQ frame lost? Again, I would need to tell you, for example, the second data frame is lost. In reality, it depends upon the conditions on the link. We normally cannot predict which frame will be lost. It may be random. Maybe 1% of frames sent are lost. So we randomly choose frames. But in an exam question, I would give you, assume data frame 2 is lost, for example. Because stop and wait is inefficient because we stop and then wait, we can use a sliding window mechanism to allow the transmitter to send multiple frames. And we get go back N ARQ. Again, more complex, but can be more efficient. We send a window of frames. Same in sliding window flow control. We can send W frames, not just one frame, W frames. If there's no error, if everything's fine, then we act as in sliding window. So we do the same as sliding window if there's no error. If the destination detects an error, we can send a negative acknowledgement. Remember, a negative acknowledgement is saying, I've received something, there's an error in what I've received, please resend, or please fix that error. A positive acknowledgement is saying, I've received it, thank you, it's okay, send me the next one. A negative ARQ indicates an error. So if an error is detected by the destination, it can send a negative ARQ, or I think in the next slide it's called a rejection. It's the same meaning here, a reject message. What the destination does then, when it detects an error, if it detects one frame is wrong, then it discards that frame, throws it away, and all future frames which have been received until the error frame has been retransmitted and received correctly. So what we do, source sends multiple frames to destination. Destination receives multiple frames. If it detects one of them is an error, is wrong, it discards that one and all subsequent frames it's received. And it sends a negative ARQ to the source saying there's been an error, send again. And then hopefully the source will retransmit and then it will receive the correct frame. We expect to receive the frames in sequence. Okay, we have sequence numbers 0, 1, 2 and 3. We must receive the data in sequence. With go back N, if there's an error, we ask the source to go back and retransmit the N frames since that error. That's where the name comes from. We go back and retransmit N, or the set of frames which have occurred since the error. And we'll see that in the slide, on the next slide. All right, there's some special case, but let's look at the general case. It's small, but you may see it hopefully a bit better on your printouts. Ignore the window size, just look, and it's a bit different than our diagrams. We don't show the transmission time just to keep it a bit simpler. We have many frames transmitted here. Frames 0, 1, 2, 3, 4, 5, 6. And in this case, B, when it receives frames, is sending back an acknowledgement or a receive ready, the RR, a positive ARQ. So B receives frame 0 and frame 1, sends back an ARQ saying, thank you, I now expect 2. It could have sent 1 here as well. That will be a different case. It could happen. 1, 2 ARQs. In this case, for simplicity or for the diagram, it sends every 2 frames an ARQ. Everything's okay. Frame 2 and 3, an ARQ comes back. Frames 4, 5 and 6 are transmitted. Because we have a sliding window, the source is allowed to send more than one frame before waiting for an ARQ. So in this case, it's sent multiple frames, 4, 5 and 6. 4 has not arrived at the destination. There's been an error. That's what this means here. 4 is lost. 3 was ARQed. Everything's okay. 4 was lost. 5 and 6 were transmitted. Look from B's perspective. B has received 0, 1, 2, 3. B does not receive 4. B then receives 5. There's an error. We expect to receive the frames in order. The source transmits the frames in order, 0, 1, 2, 3, 4, 5, 6. Therefore, B should receive 0, 1, 2, 3, 4, 5, 6. But in this case, B has received 0, 1, 2, 3, 5. 4 is missed at B. Therefore, B detects an error. Something's gone wrong. It should have received 4 before 5. So when that happens, it sends back this reject message, a negative ARQ, saying something's gone wrong. And the number in the reject message is 4, saying something's gone wrong. I expect to receive 4. I've received 0 through to 3. I've ARQed. I've said I'm ready to receive 4. I've just received another frame, 5 in this instance. Therefore, I've missed frame 4, so I tell the sender frame 4 has been missed.
We need another thing. Why doesn't B just request for 4 again, like without saying the reject?
And that's what this reject is. It's really requesting to resend 4.
So it could have been RR or
No, an RR is like a positive ARQ saying, thank you, I've received things, I now expect 4. And conceptually, a reject is a negative ARQ where we say, something's gone wrong, retransmit. And A takes different action depending upon what it receives. You could implement them the same. There are ways to combine them. But think about what the meaning of this message is. The meaning of this message is something's gone wrong because I've received 5 but not 4. Now, importantly, when B receives 5 and then a little bit later receives 6, with go back N, it discards them. It throws them away. It's waiting for 4, so anything that arrives which is subsequent to frame 4, it discards. It doesn't store in memory. It makes it simpler. We'll see an alternative later, but it discards anything since the error frame. So it discards 5 and 6, sends the reject message. Eventually, A receives the reject message, says, really it tells A, retransmit frame 4. And 5 and 6. Why 5 and 6? A has sent 0, 1, 2, 3, 4, 5, 6. The reject 4 tells A there's an error with frame 4, but also we'll need to send the subsequent messages, 5 and 6. This is the go back and retransmit the N frames. Go back and retransmit the error frame, frame 4, plus subsequent frames, in this case 5 and 6. So you see what A does is retransmits 4, 5 and 6. And they, in this instance, are delivered correctly. So if B detects an error, tell A with this reject message, discard subsequent frames, even though they're received successfully, they're not in order. So we ignore them. A will have to go back and retransmit 4, the error frame, and the subsequent frames transmitted 5 and 6, 4, 5, 6. And then they're received, and up until here at least, everything's okay. So that's where the name comes from. Go back and retransmit N frames since the error frame, since and including the error frame. Why is it better than stop and wait ARQ? Because we can send many frames without waiting for an ARQ. The same reason why sliding window is better than stop and wait flow control. Or it can be more efficient because it allows us to send multiple frames. We don't have to stop and wait here. We can send 1, 2, 3 and so on. But it's more complex. In this case, we have to retransmit multiple frames, not just one. This example shows another case as well. 4, 5 and 6 are retransmitted. 4 is acknowledged. Frame 6 and the previous frame 5 are acknowledged, but in this case the acknowledgement is lost. So in this case the data was lost. We went through a case with stop and wait, data loss, and from now onwards we're considering a case where the ARQ is lost, like we did with stop and wait. The ARQ is transmitted, but it's not going to be received by computer A. Similar, we have a timeout mechanism. If we don't receive the ARQ within some time period, retransmit. But it's more complex here. What we do is that, okay, we're expecting an ARQ, or in this case a receive ready. What the source can do is send a special message to B asking for another ARQ. This is it's called a receive ready with a P bit described here. It's what I call, or what we think of as an ARQ request. It doesn't contain data. This is a request for an acknowledgement. The frames are data frames. Because we didn't receive an ARQ, we time out. What we do is we tell the computer B, please send me another ARQ. The last one you sent was lost. I didn't get it. And we know that because of the timeout. Please send me another ARQ, and which is this ARQ request, or on the slide RR with a P bit equal to 1. And then it sends another ARQ. And from the ARQ number we know what the receiver has successfully received. And we know whether we need to retransmit or keep sending. In this case, 6 has been received, 7 received, 0 has been received. B is expecting frame number what? At this point in time, what is B expecting? In this case, we have sequence numbers from 0 up to 7. We've received 0, 1, 2, 3. 5 and 6 were discarded. 4, 5, 6, 7. 0 has been received, so the next one expected is 1. We didn't receive an ARQ. We timed out. So A sent a special message to B saying, I want another ARQ. And we send the ARQ, the receive ready, saying the next one expected is 1. So we now transmit 1 and then 2, and we can keep going.
Think about it, after every 2 frames it sends an ARQ, right? So it should have sent an ARQ after frame 0.
In this case, you're right. We're seeing that we're ARQing every 2 frames. It doesn't have to be that. We could ARQ every 1 frame, every 3 frames. It's up to the receiver when to ARQ. We could have sent an ARQ here. We could have done that. Yep.
Without requesting. So
Yep.
then this.
But it may not have helped in this case, because we would, if we sent an ARQ here, if we timed out from the previous one, we'd still send the ARQ request, because we've timed out.
So it'll discard the first ARQ.
Yeah, we would either, if we did send an ARQ here, then we'd send the ARQ request and send another ARQ back, receive another ARQ there. So from the acknowledgement numbers, we take the number that's received, in this case RR1, and that tells us what frames have been successful, the previous frames. If we did receive an ARQ here, then yes, we would know that frame 1 would be successful, and we could have kept going. Similarly, if we sent an ARQ every frame, it would be slightly different again. Okay. The point here is, if we are waiting for an ARQ and it's lost, then eventually we'll time out and request a new ARQ. That's the concept here. More complex than what we've seen in the other protocols. Okay, it's getting more complex. We've got different ways for dealing with lost acts and compared to lost data. More complex than stop and wait ARQ for sure. An alternative. Using sliding window, almost the same as go back N, except selective reject. So it's the same scenario up to here. Frame 4 is lost, 5 and 6 were sent. With go back N, 4 is lost, 5 and 6 are discarded. A needs to retransmit 4, 5 and 6. That's simple in that we don't need to store frames at the receiver, 5 and 6, but wasteful because we need to retransmit 5 and 6. Selective reject is some modification where we detect frame 4 is lost, we tell A frame 4 is lost, only frame 4 is retransmitted. 5 and 6 are buffered at the receiver. So the difference between go back N and selective reject is that with go back N, after a lost frame, subsequent frames are discarded. We do not store them in memory at the receiver. That's simple for the receiver. With selective reject, after a lost frame, frame 4, subsequent frames are buffered or stored in memory at the receiver. That requires more memory at the receiver. The benefit of this is that A only needs to retransmit frame 4. It doesn't have to retransmit 5 and 6. It retransmits 4 and then moves on to 7 because 5 and 6 have already been sent. So this requires some storage at B and some reordering of the frames at B because now we've got 0, 1, 2, 3, 5, 6 in the buffer, 4, and now take 5 and 6 from the buffer, and then 7, 0, and back to normal. The rest is the same as go back N. So there's two small variations between the sliding window-based ARQ mechanisms. Go back N, do not store frames at the buffer, at the receiver. Go back and retransmit them all. Selective reject, store frames at the receiver, only go back and retransmit one frame. The rest are the same. Selective reject, also called selective retransmission. We don't retransmit a set of frames, we select one to retransmit, or we reject one. Selective reject compared to go back N minimises the retransmissions. That's the advantage. But selective reject means there needs to be some extra buffer or memory at the receiver. That's the disadvantage. And it's more complex to implement at the receiver and the transmitter. That's also the disadvantage compared to go back N. And it turns out, even though it's more efficient in terms of retransmissions, the complexity and the buffering means it's not as commonly used as go back N. The simpler one is considered better for many applications. Some satellite links use selective reject. So go back N, frame detected, it lost. Go back and retransmit that one plus the subsequent ones. No need to store the subsequent ones in the buffer at the receiver. Selective reject. Go back and retransmit just the frame that was lost. Store the subsequent ones in the buffer until later use. And that means more buffering, more complexity, but less retransmissions. And there are variations for each of them. They're the general mechanisms that can be more complex. I think for you it's important to understand the main trade-offs between, in both flow control and error control, the stop and wait versus sliding window, and same in error control, stop and wait, ARQ versus go back N and selective reject, and also the trade-off between go back N and selective reject, the small difference there. Other than that, most of the mechanisms are very similar. What have we missed? With go back n, there's a maximum window size, same as the sliding window, 2 to the k minus 1. With selective reject, it's slightly different. It's 2 to the power of k minus 1, okay? Smaller. We're not going to explain why they're different. In the textbook, there's a good example of if you have a larger window, what can go wrong. But we do not have time to go through that in this course. It needs a good hour or so to explain. So there are some difference in terms of the maximum window sizes. But I think for this course, you need to remember with a sliding window and go back n, maximum window size 2 to the k minus 1, where k is the number of bits in the sequence number. 3-bit sequence number, 7. 4-bit sequence number, 15, and so on. With selective reject, it's different. Any questions on our ARQ mechanisms? We've gone through stop and wait in a bit more detail than the others, just to give you the principles of go back n and selective reject. Yep.
Which one is better?
Which one is better? It depends upon the conditions of your link. That is, there are trade-offs, because we see the differences in terms of efficiency, complexity, and memory requirements at the receiver. So there's no one best solution. If you've got a lot of memory and you can implement a very complex protocol, and you want to be very efficient, then selective reject is better. But if you want something very simple and your propagation delay is very small, then stop and wait may be suitable, because it's simple. It is inefficient when the propagation delay is large, but if the propagation delay is small, stop and wait is okay. Okay, so there's no one best solution. In your lecture notes, why is that? The k to, on the selective reject ARQ, the k to the minus 1 is the exponent. Fix that. In your lecture notes, it's 2 brackets k minus 1. That's wrong. It's 2 to the power of k minus 1. On slide page 30, it's 2 to the power of k minus 1. Here. I think earlier we skipped over one slide, and there's a couple more, but two concepts that we haven't discussed yet. One of them, in our ARQ mechanisms, we have a timeout. Okay, before we move on, yep.
What does it stand for?
K is the number of bits in the sequence number. K is the sequence number if it's k bits long. Then 2 to the power of k minus 1 is the maximum window size. The number of bits in the sequence number is usually specified for the protocol. So this k If my protocol has a 4-bit sequence number, then I can determine the maximum window size. It's normally specified for a protocol.
So the k minus 1 is
This is correct for selective reject. The k minus 1 is the exponent. Okay? With sliding window or go back n, it's the k is the exponent minus 1. Okay? You're going to go read the textbook to find that out. 3 bits. The window size with selective reject with the same number of bits is smaller than go back n. 2 to the k minus 1, 2 to the k minus 1, where k minus 1 is the exponent, as an example. 7 and 4. I'm not going to explain or try to explain the differences, why they're different. It's too hard in the time we have. But I will try and explain 2 more things. One is the timeout. We saw with the ARQ protocols we had a timeout value. I think one of our slides later. How long should the timeout interval be? That's the question. How long should we make the timeout? Just long enough to give us a chance to receive the ARQ. If I ask you a question, what is 10,000 divided by 342? What is 10,000 divided by 342? How long do I wait for the answer? If I ask someone a question and how long do I wait for an answer before I repeat that question? That's our timeout period. How long do I wait before I retransmit that information? If I wait for a long period, I send some information, I'm waiting for a response. If I wait for a long period for a response, then eventually I don't receive a response, then I'll retransmit. The longer I wait, the less efficient I am because I'm spending some time not sending. I'm waiting. Okay? So the longer the timeout period, if our data is lost, the less efficient we are with our protocol. If I ask a question and I wait for 4 days for your answer, then it means I spend 4 days standing here waiting for you to answer the question. But if you never answer, then that's inefficient. Same as if we transmit and we have a long timeout period here, our data is lost. We're never going to get an ARQ. The longer the timeout period, the less efficient our protocol will be. What if I ask a question, what is 10,000 divided by 342? 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 What is 10,000? If I keep retransmitting, I just wait for that 1 millisecond for an answer, I don't receive an answer, so I retransmit, and I retransmit, and I retransmit. Again, I'm very inefficient because I'm retransmitting, not giving him a chance to respond. He may have the answer, but it takes some time to respond. So if our timeout interval is too small, we may retransmit before we give the receiver a chance to respond. Again, being inefficient. We can draw that. And we can draw the 2 cases. So choosing a timeout interval is difficult. So one case is I send my data. If the data is lost and I wait for a long time to retransmit, so this is one approach, and an alternative is a shorter timeout interval. Data is lost. A short timeout interval. Comparing the two, if the data is lost, the shorter timeout interval is better because we transmit the data, time out, retransmit. We only spend this time waiting. If we have a long timeout interval, transmit the data, data is lost, waiting for an ACK, waiting, still waiting for an ACK, and then receive no ACK, but we time out, then we retransmit. In these two cases, this is more efficient because we spend less time waiting. So, small timeout interval. So this one suggests we need a small timeout interval. But what about this? We send our data. Let's make it very small. Timeout. So here's our data. So I'll make it bigger so you can see at the back. A bit clearer. Send our data. There's no data lost in this case, but there's some propagation delay. It's going to take some time for the ACK to get back. There's an ACK here. So the ACK is going to get back, but if I set the timeout interval to be small, I'd retransmit here. This timeout interval would be too small because what happens, send the data propagates, eventually the ACK is going to come back, but I send it again because I time out without giving B a chance to respond. That's inefficient because I've sent the data twice now. So it hasn't improved anything. I need my timeout interval to be long enough to give the receiver a chance to respond. So if this is the response time, propagation, ACK plus propagation, the timeout should be larger than that. But not too large, such that if we lose the data, we wait for too long. It should be larger than, or slightly larger than the time it takes the receiver to respond in the normal case. The problem with this is that in real life, it's hard to predict how long it takes a receiver to respond, because sometimes the propagation delay may vary, the transmission delay may vary. So in some protocols, knowing how long it takes to respond in advance is not possible. It varies. Sometimes it's small, sometimes it's large. Whereas the timeout interval needs to be known in advance.
Does it have any particular factor that depends on?
So in this case, we see you could calculate the timeout should be at least 2 times the propagation delay plus any ACK transmission and any processing time.
So that's basic.
Yeah, it should be at least greater than this period so that we give the receiver a chance to respond. So ideally, in this case, if the timeout period was about here, then in this case the data is transmitted, propagate, ACK comes back, everything's fine. If the data was lost or an ACK was lost, then we'd time out at this time and retransmit. So it should be greater than the time it takes for the receiver to respond. If it's too long, waste time waiting, If it's too short, we retransmit when we don't need to. So that's about what's a good timeout interval. It's the same, most protocols have a timeout interval. When you access a website, you type in the URL and press enter. If that web server is not available, not accessible, then eventually your web browser will show an error, could not connect. How long does it wait before it shows you that error? Well, that's a timeout interval. It needs to be long enough to give the chance for the web server to respond, but not too long such that you wait there waiting forever. Okay, so you need to choose an appropriate value. What else? One thing we skipped over, a long way back. How big should our frames be is another design criteria that we haven't looked at. So what the timeout interval, it depends on our propagation delay and other factors. Another thing is how big should our frames be? Let's draw some and see what happens when we use different size frames. And this applies for all the protocols we talk about. Let's say I have 10,000 bytes of data to send. The question is, what's the impact of using different frame sizes? Let's say my frame size allows me to have a full 10,000 bytes of data. So this is the original data. Let's say the frame has an upper limit saying that I can have no more than 10,000 bytes in it. So I create a frame. Has 10,000 bytes plus a header. An alternative, if I had a frame size which had a limit of 1,000 bytes, then what I would need to do with my 10,000 bytes of data, I'd need to create 10 different frames. Let's try and draw them. We have 10,000 bytes of original data to send. Let's consider two different cases. What if our frame size allows us to carry 10,000 bytes, the first case, and the second case, what if the frame size is limited to 1,000 bytes? In that case, in the first case, we'd need one frame plus some header. In the second case, we'd need 10 frames, each with 1,000 bytes of data plus a header. Which one's better? Which frame size should I use, 10,000 or 1,000? Which one's better? $10,000 byte frame or 1,000 byte frame? Which one's better? Second one. Why? Many portions. We only want to send 10,000 bytes from A to B. Yes, many portions. Why is that better? Good. If there's an error, the smaller frame size is better. Let's consider that case. What if there's an error in our transmission? Let's say the errors in our link, we have an error rate. When I send bits, I don't know which bit is maybe an error, but there's a chance of an error in some of the bits. Let's say the chance of an error is 1 bit every, to make it simple, every 10,000 bytes. So of those bytes that we send, one of those bits is going to be an error. Let's say, choose randomly, it's this bit here, okay? And here, actually, because I haven't drawn all of the bits, maybe it's somewhere around here, which is somewhere around here. One of the bits in all of those bytes sent, at the receiver, there'll be an error. What happens? In this case, the sender sends this one frame, the receiver receives it, finds there's a bit in error. It treats it as a damaged frame. It's received a frame which has errors. There's a problem. So a retransmission happens. In this case, we retransmit the entire frame. Even with just one bit wrong, because we operate on a frame basis, we would use, say, stop and wait or one of the other mechanisms to say, retransmit this frame. And so the source has sent the original frame plus the retransmission. In this case, the source sends the 10 frames. 1 bit is in error, same as here, 1 bit, but let's say it's in the 3rd frame. In this case, frame 1, successful. Frame 2, successful. Frame 3, a damaged frame, retransmit. So we'd have to retransmit just 1 frame of the 10 in this case. So if there are errors, retransmitting smaller frames is better than retransmitting bigger frames. Because here we need to send 20,000 bytes plus the headers. Here, 10,000 plus 1,000, 11,000 bytes plus the headers. Assuming the headers are small, we have to send a total much more here than with the smaller frames. If there are errors, using smaller frames is better than using larger frames. Okay? Someone else have an answer for me. Which one's better? A or B? In terms of errors, the second one, smaller frames, is better. What else? What if there were no errors? First one, why? Less header, okay? Ignoring the errors. If there are no errors, focusing on the blue one, let's say the header is a fixed size in all of them, it's 10 bytes. So here we send 10,000 plus 10. Here we send 1,000, 1,000, and each header is 10 bytes. So we send more header in this case. With smaller frames, the larger the header relative to the data. So if there were no errors, well, a larger frame is better in terms of the header contributes less to the overhead. Here, if we calculate, this is 10,000 plus 10. This is 10,000 bytes of data plus 100 bytes of header or overhead. So small frames are good if there are errors, but they're bad in terms of there's more header. There are some other reasons as well that make small frames better. Again, it's a trade-off. There's no one best size.
In case of error, it is the B modifier.
In case of errors, the smaller frames, the B is better.
The best way for the best protocol to use would be selecting ARQ, right?
If there are errors, you need an ARQ protocol, yes.
Selecting would be
Selective reject, not necessarily. Depends upon the number of errors, the link characteristics. Which one's better between stop and wait, go back end, selective reject? Again, there's no one best solution under different conditions. Yeah. You just need to know the trade-offs. When is one better than another, but you cannot say one is always better than the other. Same here. We cannot always say large frame size is better than small. It is when we have errors, but the bad part is that, sorry, it is when we don't have errors, but when we have errors, a large frame is not good. Okay? So there's a trade-off there. Normally, a protocol will specify the maximum frame size, and you cannot use larger than that. It's usually chosen based upon this trade-off. That almost finishes data link control. We've covered, I think, the main things that we need to know about flow and error control. And some of the design trade-offs about frame size, about timeout periods. They are general mechanisms. Many real protocols make use of those mechanisms of go back end, stop and wait, and so on. These are just some names of some real protocols, but there are many others. HDLC is a common one. They use go back end and selective reject. Point-to-point protocol has no flow control, and although we didn't cover it, uses CRC for error control. But there are others. Specifically, when we look at wired LANs and wireless LANs, we see some of those mechanisms in place. Finished that topic, but not the lecture. What's the next topic? I think you're on your new lecture notes, part 2. We've covered before the midterm mainly physical layer, sending signals. We've looked at some parts of the data link layer, specifically flow and error control. Multiplexing, we're going to say very quickly something about it and then skip over this. And then we're about to move into how do we connect multiple links together to create a network. We're going to look at different parts of networking. The next topic, we mentioned multiplexing, so let's just explain what we mean by multiplexing. We're not going to cover all the slides, it's very short. We'll explain multiplexing with a very simple example and related to telephone lines. And when we talk about telephones here, we're talking about not mobile phones, but your old home landline phone. Okay? And you have your home, and from your home there's a telephone line that comes out and it goes to a local telephone exchange. Okay? And other homes, other users, also connect into your telephone exchange. So there may be a telephone exchange for some area, okay, where there are many homes or many users connected their telephone line into that exchange. So the exchange is some building with some equipment inside, and all the telephone lines for the nearby homes all connect into that exchange. And you have many exchanges across the city, across the country and across the world. And the exchanges connect with each other. Here's a simple view. One telephone exchange A, and let's say that there are 1,000 homes or users connected into that exchange. So there are 1,000 lines coming in. Okay? So 1,000 people may pick up their phone and make a phone call. And let's say for simplicity, okay, these 1,000 people make phone calls and the destinations that they call are all on telephone exchange B. Here are some other users somewhere else in the city. Some other homes or houses. So they have their, usually a copper twisted pair cabling going from the home into an exchange, maybe over a distance of several kilometres. And then there's this other telephone exchange somewhere else in the city and the people connect into there. So this user makes a telephone call to this user, for example, and so on. So the people on exchange A call the people on exchange B. We need to connect the two exchanges together. Okay? The telephone calls, think of when someone's making a call, is the data we want to communicate from source to destination. We need to connect exchange A to exchange B. The question is, how do we connect? Well, the first option is that we have 1,000 cables going from A to B. Okay, so the exchange, do not draw this or we'll see why it's wrong, but telephone exchange here, so these are cables, copper wire, twisted pair cables from a home to an exchange, and for every user on exchange A that may want to call on exchange B, we have an individual copper wire going from A to B. Okay, so 1,000 copper wires going from A to B. That would allow this person to make a phone call. Their data would, their signal that they send representing the data would flow across this line to the telephone exchange, and then through the exchange and across this line, the telephone call. Sorry, I haven't connected well. So when they pick up the phone and start talking, this signal represents the data being sent from when someone's talking to the person here. And when someone else calls, it uses the second line and the third line and so on. How many telephone lines do we need here? 1,000, okay? 1,000 users here want to call 1,000 users there, 1,000 lines here. So we have one part of in Bangkadi, and then it runs it, 2 different telephone exchanges. We connect them together using 1,000 different cables. Not very convenient to have 1,000 different cables all between the same site. What would be better is to have a single cable that carries all of the data from those telephone calls. Okay? Instead of having a separate cable for each telephone call, each piece of data, combine all the data onto a single cable. That would be more efficient in terms of building and deploying those cables. So instead of having 1,000 cables, let's maybe use an optical fibre which supports a much higher capacity, and replace those 1,000 cables with one cable which has a higher capacity. Okay, that would be better, because then we just have one cable and it's designed such that the capacity is enough to support multiple telephone calls. If we measure the capacity in number of lines or the number of voice calls, normally we measure the capacity in terms of bits per second, but if we simplify and say the number of telephone lines or voice calls, what should the capacity of this line be, of this cable? What should the capacity be? If one telephone call uses a capacity of one line or one voice call, what about our one between the two exchanges? What should the capacity be? Again, 2,000. Why 2,000? You said 2,000, that's close. There's a reason you said 2,000. Why? Going back, all right, you're too far ahead. Let's keep it simple. Let's just go in one direction to keep things simple. So if we're all talking in this direction, I know it's not real, but let's consider just this direction, then we think, okay, if there are 1,000 different users, we'd need enough capacity to support 1,000 different telephone calls. Okay, so we'd get a technology which has a capacity of 1,000 times one of these. Okay. The process of taking the data from multiple input lines and combining that data, so we have multiple signals coming in, okay, from different users, and they're all combined and sent across this one line. This process is called multiplexing. And we send a signal representing all 1,000 phone calls to the exchange B, and that does demultiplexing and separates out that one receive signal into the 1,000 individual lines. So this is our concept of multiplexing. Rather than having individual lines for each separate piece of data coming in, each separate voice call, use a single line and combine the data and transmit it as some signal across that single line. So that's multiplexing. Now, we said that the capacity of this line should be 1,000. Let's add some more details. And we see that where the benefits of multiplexing come in. We have 1,000 lines. We know on average one person makes 2 phone calls per hour. Okay, on average, one person every 30 minutes they make a phone call on their telephone. And the average time for a telephone call when they make a call is 3 minutes. Okay? Let's just say that all the users have that same pattern. That is, every hour they make 2 calls and each call lasts for 3 minutes. So for this telephone line, over a period of, for just this user, over a period of 1 hour, how much time are they using the telephone line? For that one user, if we measure over 1 hour, how much time are you using the telephone line? 6 minutes, 2 calls per hour, 3 minutes per call. So you pick up the phone, talk for 3 minutes, put it down. 30 minutes later, you pick up the phone, talk for another 3 minutes, put it down. So we'd say every hour they are using the telephone for 6 minutes. That's this user, okay, if we have these statistics. And similar for other users. Every user uses their phone line for 6 minutes out of the hour. Or 6 minutes every hour is, what, 6 divided by 60? 1/10 of the time. Okay, so we could say every user uses their telephone line 1/10 of the time. The other 9/10, they're not talking on the phone. They're not using it. We need a telephone line from our home to the exchange, okay? Even though we only use it 10% of the time, the user needs to be able to use it whenever they want. Now, come back to what is the capacity required for this line, this link. Now, if we look at the statistics, we have 1,000 users, 1,000 input calls. Every user on average uses their line for 1/10 of the time, 10% of the time. This user talks for 10% of the time, this one for 10%, and so on. What's the capacity we need for this line to carry everyone's traffic? Well, assuming that, okay, this person talks for 3 minutes, and then maybe someone else talks for 3 minutes, and then someone else for 3 minutes, then if we have 1,000 users talking, but they only use it for 1/10 of the time, then the total amount is 1,000 times 1/10. The total amount that they're using, or the total number of lines they're using, is 100 on average. What that means is, even though we have 1,000 users here, because they're not always using the telephone line, they're not always sending data, the capacity of this line can be much lower than the total input. In this case, we can set the capacity at, say, 100 lines, and because at some point in time there's only a few of the users talking, not all 1,000 talk at the same time, then we can have a lower capacity on the link between A and B. And having a lower capacity on the link between A and B means it's cheaper. It's better for the telephone operator. So we don't need to have a capacity of 1,000 here, because the users aren't always sending data. We need to have a capacity such that on average, if we look at all of the users, how much data is going to be sent. In this case, on average, 1,000 users, each sending data for 10% of the time, we'd need to carry, on average, 100 telephone lines or 100 voice calls. The units I used here are not correct or are not typical. I'm just trying to demonstrate the point that this link, because not everyone is communicating at the same time, the capacity of this doesn't have to be 1,000 times the capacity of one of these. It can be less. And that's where the advantages of multiplexing come in. The line between two devices which carry multiple users' traffic, the capacity can be lower than having 1,000 lines through there, which becomes cheaper for the people who build that network. And that's about all we want to know about multiplexing. It's the process of combining data from multiple users or multiple inputs into a single cable or a single line. When the data from multiple stations share one link. So we don't just have a link per user, we may have a link where the data from multiple users go across that one link. And because of the statistics of the amount of time which users transmit, think of a telephone line, not everyone calls at the same time, not everyone uses their phone line for the same 1 hour. Same with web browsing. The link between our campus and Rangsit has to carry the traffic of all you students during lunch break browsing websites, but not everyone is sending traffic at the same time. Sometimes you're reading the web page, sometimes you're not using it at all. So using multiplexing, we need a link that has enough capacity to support on total the average amount of traffic coming from the students. We can reduce the required capacity. That's sort of the picture where we combine the inputs into a multiplexer or a mux. One link carries the data from all of those inputs and a demultiplexer. It becomes more cost effective by using a single line as opposed to using many smaller lines. Use one optical fibre as opposed to use 1,000 copper wires.
So for 100 lines, does it mean that only 100 users can talk simultaneously?
Yes. In this analysis, if we have this capacity of 100, it means only 100 users out of the 1,000 can talk at the same time, which is okay most of the time. Because most of the time, not all 1,000 people are making a phone call, because they make phone calls at different times. If 1,000 are making a phone call, if 100 are making a phone call, and the 101st picks up the phone to make a phone call, the telephone exchange would give a busy signal. You'd get that signal which indicates you cannot make a phone call. Sometimes you get that on mobile phones. When a mobile phone tower or the network is busy, it's reached its capacity, it cannot handle any more data into the system. That's the same concept. But that's going a bit far from what we're trying to explain here. There are different ways for doing multiplexing. We're not going to cover them. Frequency division multiplexing, time division multiplexing. And some examples. Done. Next week we'll look at the next topic, circuit switching and packet switching.